In physics, a plasmon is a quantum plasma oscillation. As light consists of photons, the plasma oscillation consists of plasmons. The plasmon can be considered as a quasi-particle since it arises from the quantization of plasma oscillations, just like phonons are quantizations of mechanical vibrations. Thus, plasmons are collective oscillations of the free electron gas density. For example, at optical frequencies, plasmons can couple with a photon to create another quasi-particle called a plasmon polaritone. Derivation. The plasmon was initially proposed in 1952 by David Pines and David Bowman, was shown to arise from a Hamiltonian for the long-range electron-electron correlations. Since plasmons are the quantization of classical plasma oscillations, most of their properties can be derived directly from Maxwell's equations. Explanation. Plasmons can be described in the classical picture as an oscillation of free electron density with respect to the fixed positive ions in a metal. To visualize a plasma oscillation, imagine a cube of metal placed in an external electric field pointing to the right. Electrons will move to the left side until they cancel the field inside the metal. If the electric field is removed, the electrons move to the right, repelled by each other and attracted to the positive ions left bare on the right side. They oscillate back and forth at the plasma frequency until the energy is lost in some kind of resistance or damping. Plasmons are a quantization of this kind of oscillation. Role of plasmons. Plasmons play a large role in the optical properties of metals and semiconductors. Light at frequencies below the plasma frequency is reflected by a material because the electrons in the material screen the electric field of the light. Light at frequencies above the plasma frequency is transmitted by a material because the electrons in the material cannot respond fast enough to screen it. In most metals, the plasmon frequency is in the ultraviolet, making them shiny in the visible range. Some metals, such as copper and gold, have electronic interband transitions in the visible range, whereby specific light energies are absorbed, yielding their distinct color. In semiconductors, the valence electron plasmon frequency is usually in the deep ultraviolet, have electronic interband transitions in the visible range, whereby specific light energies are absorbed, yielding their distinct color, which is why they are reflective. It has been shown that the plasmon frequency may occur in the mid-infrared and near-infrared region when semiconductors are in the form of nanoparticles with heavy doping. The plasmon energy can often be estimated in the free electron model as whereas the conduction electron density is the elementary charge, is the electron mass, the permittivity of free space, the reduced Planck constant and the plasmon frequency. Surface plasmons. Surface plasmons are those plasmons that are confined to surfaces and that interact strongly with light, resulting in a polaritone. They occur at the interface of a vacuum and material with a small positive imaginary and large negative real dielectric constant. They play a role in surface-enhanced Raman spectroscopy and in explaining anomalies in diffraction from metal gratings, among other things. Surface plasmon resonance is used by biochemists to study the mechanisms and kinetics of ligands binding to receptors. Surface plasmon may also be observed in the X-ray emission spectra of metals. A dispersion relation of surface plasmon in the X-ray emission spectra of metals has been derived. More recently, surface plasmons have been used to control colors of materials. This is possible since controlling the particle's shape and size determines the types of surface plasmons that can couple to it and propagate across it. This in turn controls the interaction of light with the surface. These effects are illustrated by the historic stained glass which adorn medieval cathedrals. In this case, the color is given by metal nanoparticles of a fixed size which interact with the optical field to give the glass its vibrant color. In modern science, these effects have been engineered for both visible light and microwave radiation. Much research goes on first in the microwave range because at this wavelength material surfaces can be produced mechanically as the patterns tend to be of the order a few centimeters. To produce optical range surface plasmon effects involves producing surfaces which have features less than 400 nanometers. This is much more difficult and has only recently become possible to do in any reliable or available way. Recently, graphene has also shown to accommodate surface plasmons, observed via near-field infrared optical microscopy techniques and infrared spectroscopy. Potential applications of graphene plasmonics mainly address the terahertz to mid-infrared frequencies, such as optical modulators, photodetectors, biosensors. Possible applications: position and intensity of plasmon absorption and emission peaks are affected by molecular adsorption, which can be used in molecular sensors. For example, a fully operational prototype device detecting casein in milk has been fabricated. The device is based on detecting a change in absorption of a gold layer. Localized surface plasmons of metal nanoparticles can be used for sensing different types molecules, proteins, etc. Plasmons are being considered as a means of transmitting information on computer chips, since plasmons can support much higher frequencies. However, for plasmon-based electronics to be useful, a plasmon-based amplifier analogous to the transistor, called a plasmon store, first needs to be created. Plasmons have also been proposed as a means of high-resolution lithography and microscopy due to their extremely small wavelengths. Both of these applications have seen successful demonstrations in a lab environment. Finally, surface plasmons have the unique capacity to confine light to very small dimensions, which could enable many new applications. Surface plasmons are very sensitive to the properties of the materials on which they propagate. This has led to their use to measure the thickness of monolayers on colloid films, such as screening and quantifying protein binding events. Companies such as Biocore have commercialized instruments which operate on these principles. Optical surface plasmons are being investigated with a view to improve makeup by L'Oreal among others. In 2009, a Korean research team found a way to greatly improve organic light-emitting diode efficiency with the use of plasmons. A group of European researchers led by IMEC has begun work to improve solar cell efficiencies and costs through incorporation of metallic nanostructures that can enhance absorption of light into different types of solar cells. Crystalline silicon, high-performance IIIV, organic, and dye-sensitized solar cells. However, in order for plasmonic solar photovoltaic devices to function optimally, ultra-thin transparent conducting oxides are necessary. Full-color holograms using plasmonics have been demonstrated. The silicon absorbs only a certain fraction of the spectrum, and it's transparent to the rest. If I put a photovoltaic module on my roof, the silicon absorbs that portion of the spectrum, and some of that light gets converted into power, but the rest of it ends up just heating the roof and waste. The new technique they've developed is based on a phenomenon observed in metallic structures known as plasmon resonance. Plasmons are coordinated waves, or ripples, of electrons that exist on the surfaces of metals at the point where the metal meets the air. See more at